Hello. Hello. I
Yes,
hope
sir.
I'm audible. Yeah.
Yes, sir.
Yeah,
Audible.
yeah. Shall we start?
Yes.
Okay. A very good afternoon to all attendees. And I'm Kulkarni, a practicing structural engineer from Pune in Maharashtra. And I welcome all of you. I see lots of people, maybe 130 plus and more are joining. So first, this is the 31st lecture of the eDiscovery series. eDiscovery is a webinar series to inspire India's best architects and engineers. And these webinars have been on a variety of topics up to today. And I especially thank Tata, the Tata Group, Tata Structura especially, Tata Tiscon also, for allowing me to do this. We'll be talking today about sustainable steel projects. Sustainable steel, we are all aware of the sustainability properties of steel, and I will take up some case studies which I personally thought were some outstanding structures. Outstanding structures in the sense could be architecturally or challenging structurally or challenging to construct also. And these are some structures which I thought are very interesting, and looking at them or trying to study them will change a little bit of our outlook, our views, etc. So we look at why steel. Again, we see structural steel today is one of the premier green construction materials around. It's essentially because it's highly recyclable. The recyclable content and also recyclable amount is it far exceeds any other construction material. The steel industry has also changed in the last, you can say, from 2010 onwards, and it has changed drastically. It was overall, you can say, a sort of a smokestack type of construction before. But today, overall, the manufacturing process has been really overhauled. It has reduced the greenhouse gas and overall emissions by as much as 35%. Even the water which is used in steel production is being recycled to the extent of 95%. And we can say that the carbon footprint of all the major steel producing countries, its footprint will continue. And again, as we see steel, because of its scalability, its sustainability properties, its properties of having both tension and compression effects together, have helped all structural engineers and architects in devising and designing various new you can say geometries for structures or new contents. Here are some of the material attributes that you see. Recycled content in steel is as much as 93%, and 98% of all steel manufactured worldwide is recycled. Again, steel has a very high strength to weight ratio, a very low carbon footprint, and as you say, it's main nowadays being used for commercial structures, etc. The main potential for it is that it has reuse and so scrap value. We can build a building, and after it has lived its life, we can still get at least around 20 to 30% of its cost as scrap value. So that is what it is. It makes it a far superior building material nowadays. And again, now the steel industry has changed. We see water up to 95% water is being recycled. Also, we see that the use of water has reduced drastically. You can see the changes since 1980 that have happened in the steel manufacturing process. You can see that a drastic change has happened. You can say it has really turned around. You can see that the decreased greenhouse gas emissions, etc., are down by nearly 45%. A decreased carbon footprint by 36%. Energy intensity per ton is nearly 31%. So that has made production of steel, especially, a very rewarding, you can say, manufacturing process. Again, its biggest application is that it doesn't have to be prepared on site. It doesn't have to be cast. You don't have to worry about its qualities. It is available in plates, in different rolled beams, whatever sizes you want. It can be fabricated anywhere and transported to your locations. Again, when you manufacture it in the workshop, you can stick to stringent tolerances. You can have erection schedules, etc., etc. And so all those things are very important. Again, wastage, which is a common factor. We see on other sides the wastage is as much as 3 to 5%. Here we can say there is hardly any wastage, and any wastage that is generated, in case it is generated, is again recyclable. Then again, as we see, we have centralized or offsite fabrication, which minimizes employee travel. Again, travel has today become a big issue with sustainability issues. And we have lots of fabrication technologies, greater precision, greater productivity, safety again. I mean, manufacturing on site also had lots of safety issues, and steel can very easily be transported by truck, rail, or barges, or ships also, because there is very less chance of it being damaged during transit, unless we are using very thin sections, etc., etc. Again, as I said, the main issue nowadays of with steel buildings is that they can easily be deconstructed, and we can, I mean, it has generally, you can say it has lots of scrap value. And in case our members are designed properly, we can literally deconstruct them and use them elsewhere. So it's not just scrap value, but we can use it to its full value also. The maintenance required is also minimum. The steel frame buildings which we see nowadays are highly durable. They have a very long lifespan. They can be very quickly modified or expanded, and also the construction sequences are you can say very flexible. I mean, you could have one side where you could do the third floor, and another side where you could do the first floor. Maybe you could skip 2 floors, do the upper floors, then come back, do the lower floors, and so many different areas. The net sections that we see for structural steel are again much lower than if you can compare it to concrete. The sizes are a lot lower, and so again we have large areas, large windows. We can have more and more open spaces. All these glass buildings that we see are essentially possible mainly because of structural steel. We will go on to some case studies. Again, as I said, there are thousands and thousands of structures all over the world which have great value. But again, this is something which I have among so many structures that we see. I like them, and since, of course, I mean, there are many different structures, many different types of structures which could be featured. But again, we are restricted on time. So what I've done is I have to try and pick out from some things. Again, as we say, the choice is very difficult. But I have taken some structures which are essentially, the first structure especially is a very minimalistic structure. I mean, it will not impose itself upon the nature or its environment, but involves a lot of design, a lot of thought process has gone into, though it looks like a very simple structure. The next structure again that I'm going to talking about is a very famous structure. It was built as a landmark or as an iconic structure. And then we could, during the course of the presentation, look at some of its construction characteristics, or maybe even the design characteristics, and I mean how out of the box thinking was necessary. Then maybe another industrial structure where the owners were very particular that everything should be sustainable, should be green, but still how they were able to generate a different type of structure without having any restrictions on the design, even the adaptability, the shapes, the sizes, etc., etc. So we'll start with the first structure that you can say I have liked, which gives me lots of inspiration because it makes you think. It's even though it looks like a very simple structure, it a lot of thought process has gone into it, and though it is seemingly simple, it's also very complicated. I mean, though a paradoxical statement, but you will see for yourself. This is the engineers were TIS and partners. It is a park keeper's flat and public lavatories, Shumdu-cho, in Yogo district in Japan. Shunai Endo Architects Institute was there. And I will just show you one sketch. This is you cannot say that is a building, but yes, this is the type of structure. And it was built as a park attendant's office, you can say, park keeper's office. And it is just a rollover. It's like a ribbon of corrugated sheets moving all round, you can say moving between two cylinders, and they have generated spaces where one is a flat for the park keeper, the other is a men's toilet, and another part is a ladies toilet. The facility, again, as we say, is a small attempt towards a new type of architecture. Architecture, you can say, which is realized by a continuous interplay between the interior and the exterior, and the interactive effect also of partial sharing of floors, roofs, and walls. And you can see here the interior and exterior, they sort of form a linkage of changes, you know. You would say it's like a challenge to the architectural norms expected by the observer. And it's a totally new, you can say, a heterogeneous architectural form. The interior walls again double as exterior ceilings and floors, which also extend as exterior walls and roofs, and one again turn into interior parts. I mean, the same part, which is the roof, turns down and becomes the floor for the next floor. This is again a part plan of the structure. We go back. The architect has used corrugated MS sheets or iron sheets, which previously were used a lot by an Australian architect called Glenn Murcutt. But again, these sheets are not supported by any means. They are just joined together and bolted together in a particular form. This form is a sort of a spiral, you can say, and the spiral is supported in a variety of ways. It's again a series of beams which are held onto steel tubes, one pair for each element in the spiral. Occasionally, the shape is maintained by an array of 7 or 8 horizontal struts. The base of one spiral is supported by a cantilever beam. I will just show you this. Here you can see we just have some poles or some what we can call as columns, then some horizontal beams. Those horizontal beams just help in maintaining the shape of the structure, and in sometimes, you know, helping the structure move around it. And sometimes these shapes, you will feel that for this size and this shape of a structure and this weight of the structure, the sizes are a little heavier. But again, these sizes are again a consequence of the Japan's, you can say, earthquake related building code. The pre-curved sheets are just bolted together side by side and also end to end. So in between the sheets, you see these, you can say, the spaces being generated, and these spaces are what are being used. You see here that this building, though visually it's a little extreme, it involved very little structural input. You know, hardly there. We just see some columns and beams, and those are just necessary. But no special significance was necessary because the use of the corrugated sheets, and the sheets are just, I mean, merely functioning as providing local stiffness in parts. The supporting structure would look odd. It has no, you can say, design value as such, the design structure, but it is just a simple metal version of, you can say, a familiar post and a beam. The sheets are again bolted together as if they would, we use it everywhere as an industrial material. But the fun part is how was this derived? Here you can see we have a column and a typical beam, and this is what I'm saying. The sizes of the columns and beams would seem to be much larger than we would have expected for such a thin and such a lightweight structure. But again, that is, as I said, mostly due to Japan's. Again, this is a study of how it all started. You can say how we are going to roll those corrugated sheets and prepare that sort of a structure, where though the use is linear, you can see here, but the structure just curves around everything. This is again an attempt to take sections of this. I will show you this, and again now we are going to have sections 1 to 10 at various levels. You can see x1, x2, x9 are the sections, and you see what sort of sections are generated in that. So we take these sections at equal distances, and this is what we get, and we try to superimpose these sections uh, over one another, and then we get the real form of it. It's Though it looks very simple, I mean, this structure looks very simple, but generating this form or trying to do something, and something that is just propped up by a column or propped up by a beam, was very difficult. I mean, this series of, again, you see that these are the studies that were being undertaken while the design was being formulated. This design is about random ribbon arrays, and how those ribbon arrays would help in generating the necessary stiffness for the sheets. The sheets by itself have strength only from the corrugations, but the corrugations and the curvature both add to the strength of the structure. So you see the various you can say geometric complexities that actually had to be tackled while doing this sort of a structure, and these are some of the experiments that were done. You can see a ribbon being passed over three cylinders, and the generated volumes in between those cylinders was then quantified and put aside. You can see one here was the lounge. The second part is the men's toilet area, and the third is the women's toilet. So this is actually how it looks. And because of these continuous changes in the geometry, this part of the structure was put up on a sort of a earth berm, so that the level differences in levels could be negotiated during the structure. Again, a little more study of how this whole thing was generated. If we look at it in plan it looks very simple, but that is not the case. You can see the curving geometries of the ribbon, the geometry involved in all that. But it is not just in plan, but it is curving in plan and elevation, and also in the third dimension. So if you try and put this plan, the first sketch that you see on the left side, on to a vertical elevation, you can see that this plan itself is moving all around. Also, it is going up and down. So if we take a section through, which is, you can say, passing through all the centers at different levels, then again we come back to that same plan, and those areas are what are being effectively used actually. So I thought this was a fantastic structure, in the sense it is, though it looks very simple, its construction, in fact generating a geometry for it, was really very difficult, and the studies that have gone into making this into a stable and a very simple structure was really very impressive. So again, if you see the effect on the surroundings, it is a park keeper's home. So the whole park, I mean, there is no chance that the park is anyway overshaded by this structure. So that is why I thought that this is among the very good structures. Next, I will go on to a very famous structure. This is the London Eye, you can say, which is located on the south bank of the Thames, opposite the Houses of the Parliament, and it has become nowadays the world's biggest observation wheel. It was actually proposed to be put up during the new millennium. It was conceived by the architectural practice of Marks Bakerfield in a competition run in the early 90s. Actually, nobody won the competition, but the architects pressed on, and eventually in the early months of 2000, it was formulated. That is why you see so many people of different companies being involved there. And yes, it was a group effort, you can say, but something really spectacular was put up. Though spectacular in terms of, not in terms of here, as we say in terms of architectural geometry, etc., etc. But structurally, this was a huge challenge because, as we see, unlike most Ferris wheels that we designed, which normally have supports on both sides, maybe everything that we have, maybe it could be a bicycle, it could be a motorcycle, or any wheel, so to say. Either we have two wheels joined together, or if we have one wheel, it is always supported from two sides. But in this case, the London Eye is supported only on one side. The whole wheel is around 135 meters in diameter, and the whole load is carried by a giant bearing which cantilevers from a pair of inclined props which are anchored out into the ground. Here you can see them. We have those two inclined props are only on one side, and there is a small cantilever which drives the whole wheel. There are 32 capsules actually, in which at least around 20 to 25 people can be comfortably seated. I'm giving you these figures for you to get an idea of the scale. From the photograph, it looks like a simple toy, but every capsule inside has capacity of holding at least 24 people. These capsules are about, egg-shaped structures, glazed. This whole wheel is rotated by a drive unit, which is actually based at the base of the structure. Here we have a drawing of the whole structure. A section. Again, this being supported from one side, it had to be anchored by two big cables. This whole concept was developed by an architect, Jane Wernick, who, not an architect, but she was an engineer with the last, we can say, the world's largest consulting engineering group called Overhoop and Partners. And they worked at infrastructure, environmental impact, and these are some very early, so to say, capsule ideas of the design. The whole concept had been designed, but you can say the structural design had not been carried out. And they were looking for some contractors or somebody to sponsor the whole project. Later on, British Airways got involved, and British Airways decided that they will help in building this. And later on, the whole process started. And I mean, when these two major contracts were established, then the engineering design started, and the engineering began with Allott and Lomax. The engineering issues were actually very complicated because there was no, you can say, there was no sort of a precedent for this sort of a design, because the shape itself was unique, the supporting arrangement itself was unique, and the engineering issues were so complicated because, I mean, the conventional codes were of no use in trying to design this sort of a structure. And so Allott and Lomax had to deploy a lot of, you can say, lateral thinking, out of the box thinking, and use of lots of advanced computer programs before they could finalize this whole thing. In fact, this finalizing or this design finalization was literally going on. It went on nearly, up to the erection stage also. And the biggest problem was that the passenger safety in this case was the very overriding issue. And you can say there was a need to check everything. As the engineers during those times would say, that there was always an underlying concern that any novel structure, that something perhaps could have been overlooked because we are doing this sort of a structure for the first time. And there is this chance that okay, maybe we've not thought of everything, since the codes are not applicable, so we have not gone and say that okay, all the conditions in the codes are satisfied, so normally we could get something stable. But it was again, this whole designing process was very transparent and very collaborative, and it also involved a lot of testing, and also intensive monitoring had to be built into this. I mean, there were several ideas about the structure. This was one of the ideas about how the whole thing could be put up. The Arup engineer Jane Wernick has prepared the sketches of how the whole thing could be set up. You can see in the left side sketches where first the foundation would be done. Next, the poles, the inclined poles would be put up. Those inclined poles could be put up, and then we would have a quadrant of the wheel put up. The quadrant would then be shifted. Then the next quadrant would be added, and so on and so forth. And then the whole thing could be, put up vertically. But after lots of deliberations and after lots of designs, it was realized that that is not possible. It will not be possible to build it up in bits and pieces, because the whole geometry as it was there, and also to estimate the wind loads, etc., would be very difficult. So it was decided that the whole thing would be prefabricated on the ground itself and pushed up. So you can see the whole this final design of this whole Ferris wheel, or you can say the rim. The rim itself is a triangular open lattice sort of truss in the form of a circle, and the circle, it being a circle and a sort of a lattice truss, that gave it the most structurally efficient solution. It provided required strength. Also, it provided lots of torsional resistance, and also a huge potential for some load redistribution. This rim is attached to the hub of the main wheel, you can say, by radial spokes. All these spokes are cables, and they are basically pre-stressed. And there are about 64 cables, and all cables are in some sort of a tension, whatever may be the rotation of the rim. This is not like our normal bicycle spokes where some are in tension and some are in compression. But in this case, all the 64 cables are always in some sort of a tension, and because of this, the rim is always under constant uniform compression. And this compression is modified a little bit by the gravity, but the rim compression is actually lowest at the top of the rim, which is quite, you can say, common sense. But the pre-stress load on the cables was or is predominantly very significant, and the load factor the engineer selected was as low as possible. So only a few cables would slacken as the wheel rotates. So you'll normally not see any cable which is sort of sagging, etc. And also, because of this you can say truss type, open lattice type of structure, a lot of rainwater and ice would be retained on these structures, and ice also was retained even on the cables, and that would change the shape and the loading. And again, the cable's natural frequency and also the damping would affect its vibration. And again, that they realized was the biggest issue. Here you see a typical connection for the cables being connected to the rim. And what you see here in the next photograph is a damper. These dampers were required because of these changing properties of this whole wheel due to the different types of loading. As we said, these dampers were added to every cable, and one strand of wire was omitted to create a small spiral path down the cable, and that would again discourage the water droplet alignment, etc. Wind loads in this case were very significant, and they realized that they were literally destructively amplifying the natural frequency of the structure. Again, that led to a lot of debate about how we have to dampen the wheel structure, and that is why again we see 64 mass tube dampers were attached. These are fixed to the outer rims. In this you see that long round cylinder, or I will go back and show you one more photograph. Here you can see these the rim has these mass tuned dampers attached to every cable location, so to say, and these were necessary for it to keep the whole thing in place when in action and also when not in action. Here you can see in this photograph the whole thing was assembled on the ground on the river, and as it was assembled, nearly you can say 2/3 of the Thames was occupied by this whole thing. And these dampers could be tuned, and these were tuned as the whole wheel was being erected. Normally, we find that in all other Ferris wheels, the passengers are normally suspended, or the seating for the passengers is suspended. But this was not the case. You can say that the sheets were aerodynamically, the seating or the cabin dynamically designed, and again they offered lots of comfort to the. They would not sway from side to side, but they would just move round and round, and that is why you would again here feel that the design of the capsule looks to be very heavy. But again, this had to be, you can say, so to say, aerodynamically stabilized, and that is why this sort of a design was necessary. Though you can say they are a little circular in cross section, so that they can rotate within the two mounting reels attached to the outer reel. And they are again driven by individual motors. Those motors are located in a void under the capsule floors, and these motors are regulated by radio signals. So you can see a very intricate design, one of its kind, was generated. These are some computer model photographs. You can see a full-size prototype of the capsule showing the fixed ring, and this was necessary to give it the, this shows you the deflected shapes of the structure. You can look at it. I mean, it is literally deflecting in any and every way that is possible. And these deformations had to be taken care of. These deformations were again very dynamic, because these deformations would change depending upon the position of the wheel. I mean, you see in the third picture, the is the straight position of the wheel. But in the remaining three diagrams, we see that the whole thing is twisting, not only in a vertical axis, but in a different. This is like, you can say, you can say the mode shapes which happen for a building during earthquake also. So the response of this structure was so dynamic, and so all the mass tuned dampers that have been provided had to be really controlled, and they were necessary. Otherwise, one would have thought, what is the necessity of having 64 tuned dampers? But these dampers were really necessary, and this is what put the whole thing in place. And this is what is giving relief to the passengers which are sitting in the in the wheel. And yes, they add to the safety also, but otherwise, with these sort of deflections, the ride. So that was about the London Eye. We will go on to another. This is really we can say a conventional project compared to the two previous projects that we saw. This is by Nicholas Grimshaw, the RAC Regional Control Center. And this is a sort of a, you can say, a car park. A car park is part of the whole building, and the building is totally glazed. I mean, no walls as such. And this is an image of the building. The outward external tiling, you can say the outward tilting external wall is shaded by the external walkways. The walkways also are used as maintenance access and also act as sunshades. You can see the silver gray roof overhangs. It allows maximum views and maximum daylight without a glare. The external wall will transmit the load imposed on the glass and the external walkways to the inner parts of the steel structure. This whole steel structure, again, partly cable stayed, partly steel. And here we see the colors of the building are deliberately kept neutral, so that the building can provide a transparent framework for human activity. This is an elevation to the building. There is an open staircase which connects all the structures, and then we have a central core which goes up. It's a sort of a, you can say, a transparent skeleton that shows all the activities that take place. Here you can see, I mean, it's everything, the whole structure, or you can say the skeleton of the structure, is so visible But internally, if you see, there is a central core again connected by the staircases, and that staircase is effectively connected to all the floors differently. Here again you see what we require for structural steel structures, again, which as against maybe conventional RCC structures or any other wooden type of structures, would be to, we require lots of bracings. We require bracings in the horizontal direction. We require bracings in the vertical direction. A very efficient use of these bracing systems, and these bracing systems have been introduced, so to say, as a design feature itself. Sometimes in part of tension only, or cable structures, or sometimes as metallic structural steel tubes only. The central core, which goes up again, has big cantilevers on both sides, and that is again suspended from you can say the pylon that is going up there. If you look at it, the plan is relatively very simple. At various level, it changes. The external part remains the same. The walkways are projecting out of the window, which help in circulation in the whole building. So we have a central core and everything built around it. Here we see, and the central part, you can see the structural steel structure itself, the rafters, the beams, etc., are used directly as elevation, and they produce such a nice effect. And their connections, etc., are so meticulously planned. The connections of the cables and the connection of the steel sections to the main structure itself, with a different geometry given to the stiffener plates, with the I-beams and the maintaining the shapes, everything is visible here. So there is no attempt made anywhere, but still we find that it gives you such a nice structure. And these walkways which are form a sort of again a vertical truss columns, and that is only trusses. Hello, hello, hello. Am I audible? Hello. I think. Can you hear me, or the connection is lost?
Yeah, Mr. Balkuni, you are audible.
Okay, okay. Shall we go on now?
Yeah, sure.
I got somehow a message saying that the connection is lost, and so I was worried. Anyway.
No, yeah. I think the net is a little poor from your side. That's why.
Oh, acha. Okay.
Yeah.
So these are some sections and some plans of this building. As you can say, it is just a glass-clad building, and the whole skeleton is entirely visible. And the steel sections itself give a sort of a aesthetic value to the whole structure. Though yes, geometrically the shape is also very interesting, but again there is no attempt to in any way hide the constructional details or the constructional or cross sectionals or the shapes of the structure. Again, we can see the connections, especially the pylons originating, and the trusses or the truss system that has been generated to support the facade, the glass facade, also has been done interestingly with the base and the formation of the pin and the shape of the stiffener plates and its joinery to the cable patterns. Also very interesting. Here you can also shape the glass and the railing also. Railing takes a very interesting form in this case, and it has also been very nicely designed with those vertical mullions, etc. And overall you get that effect that it is just steel, steel, steel and steel. And again, maybe the people who are working there would get that effect, that all the time they get fantastic views of not only of the outside but also of the inside. And as the sunlight changes, the glare, or the light inside the building keeps changing. So it's always very interesting. I mean, any person, all the people who are working there would find it so interesting that, I mean, it's like through the day they would have different views, and they would get that feeling is that we are working in a different environment, you can say, throughout the day, not a constant view all the time. You can see the cantilevers, the cantilever brackets that are provided are also very elegantly done. So that was about this. We'll go on to another a warehouse, which again I liked. This is also again from Japan's Nagasaki district, and this was a recent, you can say, a landfill pier. And this structure overall is about 800 feet in length and 400 feet in width. I mean, 800 feet in length and yes, 400 feet in width, and it projects into the Nagasaki harbor. This entire pier, so to say, this is a sort of a warehouse and also a pier. It has a mixed use. It's a terminal building, large, some retail structures in it, and it has some working warehouses also into it. The view that you see on your right hand side is again the city, the outlying mountains, the bay which is surrounding the site, and you can see that this whole structure is very visible from everywhere around. And around the harbor, you can see the site can be viewed by many passenger ferries, ocean liners. You can, all these things which so to say link Japan with the world. And with all this in mind, the architects had proposed a rooftop public garden space in addition to the 14-meter high two-level warehouse that was commissioned actually. Warehouse, we have some different warehouse C, which is again 200 meters long, 25 meters wide, and you can say average of 22 meters high. You can say these dimensions of the warehouse are literally comparable to a tanker, you can say, a super tanker. And this whole thing is organized in 3 different parts. It's a 2-level private warehouse on the bottom, a public garden on its roof, and a 20-meter diameter spherical exhibition hall. The round shape that you see, this is the visibility of the whole structure, the pier. The roof shape, it's a, you can say, a sort of a elevated ground floor plane, and it provides a sort of a public link between the ferry and the retail spaces on the new wharf, or you can say some roads that lead to the center of the city. This again is not entirely steel. It's a sort of a composite construction. The warehouse is concrete. The south elevation walls, systems, and half, you can say, approximately half of the roof enclosure is fabric on the north side. And the spherical exhibition hall is insulated steel. It's about 20 meters in diameter, and it is actually used as a petroleum storage tank for the huge tanker ships that come into Nagasaki. The steel, this steel actually shields the whole building from the prevailing, you can say, wind storms that occur here normally in the monsoon. The steel structure, the plate wall, the roof systems, and the steel spear are actually manufactured by shipbuilders across the harbor and brought to site by a barge and assembled together here. The roof and the walls of this whole thing are a series of parallel frames. I will just show you the roof. Here are some photographs during the construction stage where the whole steel pier was fabricated elsewhere, brought to the site, and actually effectively lowered in place by the steel barges itself. So this has not been fabricated by standard civil engineering fabricators, but the the whole thing has been constructed essentially by shipbuilders. Again, we see a contrasting style here for construction of the warehouse, where one side we have a regular a rolled beam, or you can say a three-plated beam system, a rafter in place, and half of it again connected to that same structure is an open web, a truss sort of a system. But this interplay and the changing spans, you can say there are no finite spans for the whole structure. It is partly covered, partly open. Again, you can see three trusses of one span. Then immediately we go on to another span. The same detail is repeated, but as we go on, the roof is at different levels. You can see all the trusses, or beyond that, the roof is again a series of interestingly, here we see that the roof is also not in one level. The slopes are different and they keep changing. This is the elevation from the seaside, and the roof and walls are again shaped by a series of, again, these are all non-parallel frames, you can say, and essentially divided into 4 different types of zones. Each zone has a different, experience of its own. As you are walking along the zone, the change in the structural system itself, you would come to know that yes, this is that we are entering a different zone, and a sort of a different form is generated from this, you can say, twisting and undulating geometry of the fabric that is covering the roof. And the steel and the planar systems, it's a big sort of paradox. It's a difference between the plane geometry and the fabrical roof. Again, it's some of the shipbuilders say there were saying that the whole thing is extremely conventional. While if you look at the structure, we see that it's hardly conventional. It's very extremely unconventional. Here you can see a typical section where the roof itself is, cascading in and out, up and down, and every face of the roof or even of the wall is a sort of a parallel frame. But inside, as I showed you, it is divided by or supported by different types of frames in the columns. In plan, if you see the garden level plan, we see that at least the columns are in a grid at one time. But if you look at it at the ground level, we can see that the columns, though they are in grid, the supporting trusses for the roofs are off grid. Again, I mean, we would normally have connected a series of columns in a particular line with a truss, but here we find that alternate columns are, in some cases, are connected directly in line, and in some cases they are connecting offline. Here again we see the different sorts of parallel frames that are generated by this, you can say, non-sequential combining of the roof structural systems. And then again we have this huge structural steel spear which is mounted on these, essentially on these main 4 columns in you can say in the area marked A. So this whole warehouse, so to say, is divided into these 4 parts: A, B, A, B1, B2, and C. And again, we see A is it's all, you can say, oblique lines. B is again a series of parallel lines. B2 is again a series of just some very small inclinations and some very big inclinations. And C again has a different plane altogether. So combining all this in one section has made this whole structure very interesting, and that is why I find it very profound. I mean, a warehouse could have been designed so simply by just taking 2 columns on one side and providing a different sort of roof, but to be able to play with this structure so much and generate all sorts of so to say structural systems to support the roofs has made this whole thing very, very interesting, and that is why I find this inspirational structure. I think these are the 4. I thought, how are we on time? Okay, it's 4:50. We have some maybe 5-10 minutes more. Shall we take some questions in case anybody has any questions? Can you see the questions here? No. Hello, Deepal?
Yes, sir. Yes, sir. So we got quite a few questions. So
Right.
one of the questions is that by Faiz, what are the some tips you can give to add elements of sustainability to structures? Some structural tips or architectural tips for adding sustainability to structures.
Yeah, basically, I mean, sustainable, it would start with selection of the material itself. As we say, when the whole part of the whole premise of, selecting structural steel was because of this, the biggest use of it being all the components of steel being recyclable and reusable. I mean, for me, sustainability would be more on these two issues. I mean, there are different parameters as you saw in the beginning of the presentation. But for me, as far as I am concerned, I would give maximum importance to do these two features, like recycling of all the, you can say, inherent materials there, and again, reuse of all of them. Like steel, we can reuse the whole scrap, or most of the materials. If we melt down the scrap, then all the materials that are inbuilt, as we say, we have iron ore, we have so many other different materials, we have different additions of materials to make them into alloys, and then we can change the whole thing. I mean, we are using it right now to maybe use it as a linear structure. We could, add some more different materials, make it malleable, make it ductile, and so many different things. So for me, essentially, sustainability would be the selection of the materials. So that would decide on the sustainability part. Also, sustainability nowadays has more significance with fire. The fire hazard also has to be taken care of. So steel will have to be suitably modified, because steel by itself has a limited fire resistance. But then we can modify it and use it as a big fire retardant also. So these 1-2 factors we could be, you can say, recycling, reuse, and fire resistant could be my choice of, making sustainable structures. Yeah.
Okay, sir, one Akshay Kumar is asking for the first structure, for the one, is this
Yeah.
feasible to construct in India, because steel sheets are pretty expensive? Can we construct?
No,
Is it?
this could be constructed anywhere. In fact, these sheets, perforated sheets, are abundantly available here. In fact, we have these nowadays crimping machines also. So in case we want any particular shape, size, it is possible to do. And we will say in India nowadays, not exactly this system, but this system has been effectively used. We have a system called Proflex, which we call as a trussless system, where warehouses or halls are being built with just sheets put up in a, you can say, arch type of fashion. It could be a not 100% arch, but a semi-spherical arch also. And these sheets are crimped, or you can say corrugated, in such a way that the strength is attained, the thickness is also attained. So we have, I mean, these people are doing up to 30, 35, 40-meter spans without stresses, by just laying these sheets next to each other and, welding them together. So that is just, you can say, an ideal example of how just corrugated sheets can be used as roofing materials. But in the first example, we saw that that was so, I mean, the whole roofing system was so complicated, but actually it was so simple. I mean, that is what makes it so intriguing. So the corrugated sheets can be used. I mean, there are other variations also. If you look at it, we have deck sheets also, which are being used to generate floor slabs, or which are being used as sacrificial shuttering for producing in structural steel, you can say, mezzanines. So that is also a variation of using corrugated sheets itself. So the way you crimp the sheets would depend upon the use of the sheet. So it's not that it is not being used in India. corrugated sheets are being extensively used in India. But of course, again, as we say, everyone is giving their product a different name, you can say.
Mr. Suresh Kumar is asking this question. What are your suggestions for the best maintenance of the structures, of steel structures? How can we maintain them for a good serviceable life?
See, first thing, the biggest and the most important thing for structural steel to remain serviceable and working and having an increased lifespan is its protection. One thing is protection from corrosion, and two is protection from fire. So as we are using it or as we are fabricating it, ensure that all this fabrication takes place in a protected environment. In case your atmospheric conditions are severe, then you have to positively take care that all the fabrication happens in a very you can say controlled atmosphere. Again, primers are very important for steel. Primers, because in case there is any beginning of corrosion, we have these primers which control or change the rust into a primer itself. So a proper choice of primers, and then a very efficient and a very good system of painting the steel structures. See, this paint will add to the life of the steel structures a lot. You have to ensure that this paint is impurity free, is defect free, and very importantly, dust free. If you are able to do this in a controlled atmosphere, you will find that the age of steel is drastically increased. So, I mean, you could start with saying that the first is the surface preparation, proper slant blasting, proper grinding of steel, proper use of good proper primers, and a very controlled atmosphere painting of the structures. Nowadays, if you want to go on and provide fire protection, then there are multiple systems now available. Some people are also getting into encasing of steel, and there are lots of fire retarders available, lots of glazings, lots of additives, which will help you in making your structure fire retardant also. So I think that is the main thing. If you want to go, whatever you are fabricating should be fabricated and painted in a very efficient manner, and you should take care that during fabrication there are no holidays, nothing gets removed, and the whole process has to be in such a way that, because in case even a part of this this cover or this protective covers that we are adding are lost, that would again start the corrosion. So mainly is that, I mean, after fabrication and between the installation, the process of applying protective paints to steel would be a very important factor in deciding the life of the structure. And also, normally we find in India it is a prevalent practice that all factory inspectors, etc., insist on looking at the structure every 5 years and issuing certificates. So for us, when we are doing a structure for ourselves, if we can maintain that habit, that a new structure for the first 5-10 years you don't have to bother, even 15 years, but after that, periodical maintenance, periodical observations, periodical structural audits of your structure will help in taking the increasing the life of your structure in a lot.
Um,
Hello.
1 second. Yeah, 1 second. I'll just. So Mr. Laika Siddiqui is asking, how does a predefined architectural design, how does it affect the load analysis and combination?
I don't think I've understood the question properly. What can you repeat the question? Let us try.
How much a predefined architectural design will affect the load analysis and combinations?
I don't know what he's trying to ask exactly, but I will interpret it in my own way. What maybe he is trying to ask is that if the architect has proposed a particular shape, and during the analysis we find that that shape is not a very optimum shape, or not a very stable shape, then what happens? Maybe that is my interpretation, depending, I mean, looking at the shapes that we saw in all the presentations. Maybe if there are some, already defined geometric lines prepared, and then you have to fit your structure into those defined shapes, then many times you find that a particular shape is not very conducive for, a very optimized analysis. Many times we find that it could have been better if this slope would have been the other way around, or in case we have these curves, maybe a curve happening at the top and then coming down to the bottom would be better instead of the other way around. So yes, that makes a big difference, and I would always prefer that when you're looking at different shapes or different sizes, or as we say in the form of that Ferris wheel, when we are trying to do something which is a lot of lateral thinking or out of the box thinking is going on, then it always has to work as a team. You cannot come and say that, okay, now we have this fixed shape and let us try and put in some material that, I mean, we can get this shape. It is all we can say a trial and error process, where you start analyzing your structure, you locate the points, you try and locate them on the basis of the shape, basis of your connectivities, your connections, and also the sizes of the sections that you are able to provide. Not just the sizes, but the shape of the sections that you would be required to connect. And then I mean, you can, your iterative process will give you an optimum sort of design. Sometimes, as we see in our previous, some shapes have to be changed, some shapes have to be, or not just shapes, but sometimes the supports, the supporting systems, or the location of those systems has to be revised to get that optimum feel. All as we say in engineering terms, to generate an equilibrium during the analysis, we have to ensure that all your supports, etc., are at optimum locations. And in case they are not at those optimum locations, then you have to design the structure in such a way that those optimum locations are counteracted. Like we have these, if you have we have a counterweight to that crane. So generally, even whatever shape you decide and whatever size or structure you decide, once you feel that, okay, the three equilibrium conditions can be satisfied, then yes, then you can go on, and do the stress and these later dynamic analysis for wind or seismic, whatever is required. But it is always better that the architect refers his shapes to a structural engineer, gets them sort of verified, or gets them through, and yes, then you can really get a good structure.
Yes, sir. There are lots and lots of questions.
I don't know if it is online. Is said something about our interpretation. I mean, let's look at it.
Yes, so there are lots and lots of questions coming out in, but I think we're out of time. So we'll share the remaining questions on email with you. Okay, so
can, send the answer by email. Okay.
Yeah. So thank you everyone for being such a nice audience, and I'm very happy that so many of you are attending the webinar today, this Friday evening. And thank you. Do watch out for the next in the series. Thanks.
Yeah, and special thanks to Tata Structura for allowing us to do this webinar, and especially do this about different types of and structures in structural steel. Okay, thank you.